Okay, guys, we're almost done. We are in the trig equation section. This is going to be part 1 and part 2, but these problems you'll see right here on page 267. Those are the ones you should practice. Doesn't mean you can't try an even problem here or there to, sharpen your skills, but do notice this. For 11 to 21, they use the answer in radians, and 23 to 33, they use degrees. It's marked in the book, but I just want you to know we are solving equations. We are not simplifying expressions. Remember, an expression is what we just did. With the inverse function section, they had us find an angle that would satisfy the problem. Now we're going to be solving. So the thing is, there's more than one answer that could be true in this case. I have an example down at the bottom, but I want to make sure you get this. For my first set of examples, I'm working in radians. They ask for the solution over the interval from 0 to 2 pi. Now remember, bracket means 0 could be one of your answers. But why did they give me a parenthesis here? Well, they gave me a parenthesis because if you think of a unit circle, it starts here at 0 radians, it goes all the way around and stops again at 2 pi radians. Whatever the answer is going to be for 0 is going to be the exact same answer for 2 pi. So they're just saying, you know what, you already gave us this result. Don't worry about including that one too, because they're going to be the same answer. What does that mean? Well, let's look at what an equation looks like in Trig Town. So, once again, I am working over the interval from 0 to 2 pi. And this example right here just kind of gets the ball rolling. I want to find out what angle could I put here to make this a true statement. So when you're solving a trig equation, you're using the same tricks you know from all kinds of equations. So I'm going to get that arrow out of my way because what I want to do right now is I want to add 3 to both sides. And if I do that, that's going to cancel out. I get 2 sine x equals, on the other side, 2. And then if I divide both sides by 2, I will have the statement I want to work with. It says sine x equals 1. Now, here's the deal. If I get a statement like this, I don't need to go, inverse function. I don't have to do that to find my solution. Like this, I don't have to do this at all. If I did, I'd get x equals sine inverse 1. And then I'd go, hey, how do I get rid of that? Oh, I do this again. I would end up walking in a circle. And I'd end up still having the same x equals, sine x equals 1. I'm right back to where I started. So what do we do? Well, if it equals 1 or 0 or negative 1, I'm used to that happening when I look at the graph of sine. Come on, really? You're not going to... There you go. So let's take a look at the sine graph. Now, notice, they want me to work from 0 to 2 pi. So here's 0, and a sine graph will go as high as 1, as low as negative 1. And I go, above, on the line, below the line, boom. Well, it appears to me that the sine will equal 1 at this location. It will. It totally would. And guess what? If this graph continued on, I'd have another answer right here. If it continued on, I'd have another answer right here, etc., etc., etc. So when it comes to solving trig equations, what they're going to do is they're going to say, hey, here's a starting location, here's a stopping location. Just look for the answers in that interval. So what would the answer look like in the book? They would say the answer to this question is x equals pi over 2. Because they want me to find all solutions that would make it true, but they only want me to look between 0 and 2 pi. So just a reminder, our sine graph looks like that. There's only one location between 0 and 2 pi where I'm going to get this value to work out. So in this particular case, whenever I get a sine equals -1, or a sine equals 0, or a sine equals 1, I think quadrantals, and I also think look at the graph. Now, what would happen if I had a situation like this one? What if it said something like this? Example 2. Sine x equals, well, I wanted to put a 2 right there. 2 sine x equals 1. Now, I would start out similarly. I would divide by 2, and I would say, okay, so I'm looking at sine x equals 1/2. Now, wait a minute. This is not something that's going to end up on my graph. Let me scroll up real quick. It's not something I'm going to find here. 1/2, well, it'd be about there. Ooh, heck, sine would be 1/2 right about there. It wouldn't be over here. These are -1/2, -1/2. And I am just guessing. I'm estimating looking at my graph. So it looks to me like sine is going to equal 1/2 in quadrant 1 or quadrant 2. So what I'm going to do is I'm going to say, hey, if I drew a reference triangle here, and I said, what would this guy have to be to make this true? 1/2. Well, I look at that and I say, hey, that's just like a 30, 60, 90 type situation. And when it comes to sine of some angle that gives me 1/2, this angle inside here must be a 30-degree angle. Or they want me to work in radians, so my answer is pi over 6. But think about it. I could draw a reference angle over here because this guy right here, and like I said in the one video, they call it x prime or something. To find this angle, that would also yield 1, 2. This time it would be a negative rad 3. But that would still give me a reference angle inside here. This reference angle would be a pi 6 angle. But that's not the answer they want. I'm going to go get my red pen. Come on. This is the answer they want, because they want all the answers between 0 and 2 pi. So just think about it. If this is 0, you go all the way around to pi, take away this little sliver, you would end up with this red angle being 5 pi sixths. Now, you could check this on your calculator to make sure you're correct. You could make sure your calculator's in radian mode, and you could punch in sine of pi over 6. You're going to see that your calculator is going to tell you it's 1/2. You could also check it with your calculator, punch it in, and say 5 pi sixths. Your calculator is going to tell you 1/2. So, better than guessing and checking, embrace the beauty of the bow tie, because if you have your bow tie sheet sitting in front of you, you could just kind of do this. And like I said, after a while, it just kind of gets in your head. So when you look at the answers in the book, they're going to list them like this. They're going to say x is equal to, and then they're, ooh, that was a horrible fancy bracket. Let me try a better one. They're going to say in the book, your solutions are, and then they're going to write them from smallest to biggest, just so you know. So you have two answers that make this statement correct this time. You have two answers that make this statement correct. Now, let me go one more, because I'm on this vibe here where we have this type of situation. Example 3, and I'm not going to get too spicy here. And you might go, well, we just did that problem. We just did this one. What if they started me off with this? What makes this different? There's a sign squared there. So when I see a squared thing in there, I'm thinking, okay, I'm still going to divide by 2. And I get my sine squared, this is example 3, sorry. Sine squared x equals 1/2. What do I do in a squared situation? I cheerlead. I root. And I say sine of x is equal to plus or minus. Now think about it. Square root of 1 is 1. And then you have a rad 2 in the bottom. And I'm not going to rationalize this yet because I notice this ratio. I see this. And I say, wait a minute. I'm going to draw a reference angle. If I drew a reference angle or triangle here, I could say they want me to find this answer, opposite over hypotenuse. And I go, heck, that's a 45-degree angle. That's a 45-degree angle. But they don't want my answers in degrees. They will tell me when they want them in degrees, but I could say, okay, that's pi over 4. That's a pi over 4 answer. But wait a minute, I could draw that angle so that it ends up over here. And basically what you're going to see me do is build a bow tie. Opposite over hypotenuse. And then I go, oh, that's a -1. Then I go, hey, what is this angle inside here? This guy is going to be another pi over 4, but that's not the answer they want. They want the answer from 0 to... So they're going to say, oh, that guy is 3 pi fourths. Now, here's the kicker. I never did anything with this. I left that plus minus there because these two answers that I just showed you are the two angle measures that would give me this answer. But there are two more answers for me to find. Sine of x equals negative this stuff. So let's go back, get the black pen. If I were to draw another angle and end up all the way over here, see my bow tie starting to come together? Oh God, that's so crooked, sorry. Opposite, so now I have another prime angle. I would say opposite over hypotenuse. And then I say, dang, this still fits the bill. That's a pi over 4 angle inside there. That is a 45-degree angle inside there. But what is the actual answer they want? I'm going to get a different color pen. They want the answer that would have resulted from drawing my angle that way. And what is that? Well, that's pi over here. So I'd say pi plus 1/4 more. That answer is a 5 pi fourths angle. Wow. And I could do it one more time. Let me get blue. Let's try blue. If I go all the way around, all the way over to here and stop, I would then have a terminal side of my angle. I could draw a reference triangle. I'm going to look for this guy right here. This dude would be based on opposite over hypotenuse, but it's a negative because this is my negative stuff. That makes this angle inside here, x triple prime, that makes that angle a pi over 4th angle, but that's not the answer. They don't want pi over 4. And they don't want me to say, oh, negative pi fourths. That's not in my interval. They don't want any negative answers. So what is that answer? 7 pi fourths. Think about it. All the way around the circle would be 2 pi. 2 pi take away 1/4. I get 7 pi fourths. So This time I ended up with 4 correct answers. When you solve trig equations, you can definitely have some problems where it's not solvable. You can. But those are usually pretty obvious, so I'm not going to worry about those ones. But when you go to solve a trig equation, my first example, what did it have? It just had the one answer, pi over 2 is the only thing that made sense. Then, the second example, I had 2 correct answers because I could only find 2 angle measurements that made that true. This one I found 4 angle measurements that made it true. So if I look this up in the back of the book, they're going to say, list all solutions, so it'd be pi over 4, 3 pi over 4, and they always write them from biggest to smallest, 5 pi over 4, 7 pi over 4. And there you go. Now, I've only done a couple types of equations here. There's more to be had. Heck, we could look at something like this. Let's look at another one. What if they gave me something that said 2 secant x plus 1, and then they said equals secant x plus 3. I go, dang, I don't know. Well, trust your gut. Get the function on one side, get the number on the other side, come on, and then take a look at what you've got. Over here, 2 secant x take away 1 secant x is secant x. I already canceled this stuff out on this side. What's it equal on the other side? It equals 2. And then I go, dang, my brain does not think in terms of secant, but it does think in terms of cosine. So I go, how about cosine x equals 1/2? Now, is that a positive 1/2, a negative 1/2, plus or minus? No, it's not a plus or minus. We didn't have a square to begin with. But I do know this. If I drew, come on. If I drew a cosine graph, if I did, it would look like this. And here would be a height of 1. This would be a depth of -1. I don't want 1, -1, or 0. So this is not the strategy to employ. I don't need that. But I do know this. If I was at 1/2 and I drew a line across, I'm going to hit this thing here and here, which means I'm going to find my 2. There's only 2 answers. But I'm going to find my 2 answers. One of them is going to be here in quadrant 1. And the other one's going to be in quadrant 4. So I don't have a whole bow tie to work with here. I don't. But I know that one of my answers is going to be this angle that I generated. My other answer is going to be this angle that I generated. I just have to find out what that little chunk is. So what did they tell me? They told me the cosine of x is 1/2. So I go, well, this is a 1. That's a 2. That means this must be a rad 3. Now, wait a minute. Yeah. And for cosine here, that would be a 1. That would be a 2. This guy's a negative rad 3. Hey, but what does that mean? It means the size of this piece right here is the same as the size of this piece right here. And that piece happens to be pi over 3. Because if I were to draw that out, that's a pi third. This guy's a pi third. But the answer they want is not pi thirds and negative pi thirds. No. They want me to give all the answers from 0 to 2 pi. So that means I have to always do my counterclockwise rotation to get these answers. So the first answer is pi over 3. The angle I find right here, this x value I found, is pi over 3. But the blue angle that they want me to find is found by going all the way around. So I would say this is 2 pi. Take away that pi third. And if you have to, do it on a calculator. But if you're looking at your bow tie, you know that that's going to be a 5 pi thirds angle to get me all the way around to 2 pi. So I look this answer up in the book, and I find that the solution they have is pi over 3 and 5 pi thirds. Sometimes you get 1, sometimes you get 2, 3, 4. There's all kinds of different things you can find when you're answering a trig equation question. There's all kinds of stuff that can happen to you. Now, I wanted to do one where factoring is involved. So here's another example I want you to see. I think I'm on example 5. Here's another example for you guys to see. And it looks like some of the stuff you're going to be up against. But this one involves factoring. And what I'm going to do is I'm going to say, hey, this is set equal to 0. I see a squared thing, but here's the deal. Do you see a GCF? They both have a cosine x. So we treat it just like we did with the trinomials or binomials or whatever. I'm going to take a cosine x out of there. And I'm going to say times 2 cosine x, I'm going to work it backwards, minus rad 3 equals 0. Take a look. All I did is I took out a GCF. And when I take out a GCF, I'm going to set this part on the outside equal to 0. And I'm going to set this part on the inside equal to 0. Well, heck, this part over here, once again, if they say cosine x equals 0, ding, 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 between 0 and 2 pi, if you have to, fill in your blanks. But the answers for that are going to be pi over 2. Cosine x equals 0 at pi over 2 and at 3 pi halves. So this little piece of the puzzle contributed those two answers. And let's solve the other side. If I solve the other side, now I'm going to move this over. I have 2 cosine x equals rad 3, but I'm not done. I want to get cosine by itself, so I divide by 2. And I say, hey, cosine x equals a positive rad 3 over 2. Hey, cosine is positive in the first and fourth quadrants. So I'm going to draw a similar picture that I did in this one. I'm going to draw a very similar picture, and I'm going to look for this part of the bow tie. Now, if I already have my bow tie in my brain and everything, I would say, oh, cosine rad 3, that would be a 2, that would make that a 1, that would make this a 30-degree angle, but they don't want me to use degrees right yet, so I'd say, okay, pi over 6. And if I were to draw a different angle all the way around the outside to get to here and have a terminal side, my terminal side right there, I'd make it a right triangle. Oh, that was horrible, sorry. Right triangle, that would be a 2. This would be a negative 1. But this angle, this reference angle in here would still be a pi sixth in size. That's how big it is. So remember, I'm trying to go all the way around from 0 to 2 pi. So I would say 2 pi take away this little sliver, well, that's the same as 11 pi sixths. Now, you go to check your answer in the book. You have 4 answers that are correct. They will do this to you. They will write them from smallest to biggest. So you will notice that even though one part of the problem gave you these answers, the other part of the problem gave you these answers, they always put them in order from tiniest to largest. So that would be your solutions for the equation for x over the interval from 0 to 2 pi. My pen quit for a second there. Now, you're going to run into a couple that might be tricky for you, that you might go, dang, I don't even know what to do with this, or whatever. Don't panic. Try to be, and remember, if you get stuck, send me an email. Or, sorry, not an email. Post it on the YouTube link and say, could you give me a kick in the right direction here? And I totally will. So I've got all these problems that we've done so far have had to do with radians. Let's look at a couple where they have us work with degrees. Now, the book has a very subtle way to do this. Whenever they use the variable x, their answers are going to be in radians. So you'll notice this when you do the practice problems. Anytime they give you a variable x, it's in radians. When they give you theta, they're going to write their answers in degrees. But whether it's radian or degree, it really doesn't matter. Radian or degree, you can still, you're doing the same exact concept for this. So I wanted to show you one that is a little sneaky. 2 sine theta minus 1 equals cosecant theta. And you go, wait a minute, I don't know what to do. I got 2 separate things. Well, we know something about cosecant theta. It's the same as 1 over sine theta. So I'm going to substitute that into the problem. And then I'm going to say, oh man, I got a fraction in my problem. I don't like fractions. Well, I can bust it. It's an equation. This is an equation, so I can multiply everything by sine theta. And if I do that, I'm going to end up with 2 sine squared thetas minus sine theta equals 1, because it's going to cancel. And then this is the other part of factoring that I wanted you to see. I can move this over, set it equal to 0, because that is what we do when we're solving stuff that looks trinomial-licious. So let's move that over, set it equal to 0. And then I go, really? I got to factor this thing? Yes, you do. 2 sine theta, and then sine theta. That would give you 2 sine squared thetas back. The last sign's a minus, so I know they got to be opposite signs, but it could be the first one's supposed to be a plus, second one's supposed to be a, but I don't know. I'll check in a second. So let's put the ones in and see what happens. That would give me 1 sine x, or sine theta, sorry. That would give me a negative 2 sine theta. What's happening with my pen? That's a negative sine theta. That is exactly what I wanted. So guess what? This is how this thing factors. It factors like this. So what do? You set 2 sine theta plus 1 equal to 0, and you solve for it. Then you take sine theta minus 1, set it equal to 0, and you solve for it. It's the same tricks we've used. Instead of having x's, they have sines or cosines or secants or whatever they want to put in there. But there are really good examples in the book. I am not doing the ones from the book so that you have a variety of stuff to look at. Now, I'm going to stop this video after this, but do keep in mind, all the examples I've done were in radian so far. I'm working in degree this time, so I'm going to end up with my answers, but they're going to be degrees. So let's finish. I'm going to do this top part. Let's do this guy right here. I'm going to scroll down and give myself a little bit of room. So it's 2 sine theta. Come on. 2 sine theta plus 1 equals 0. Let me make sure I copied that down right. Yes, I did. Okay, so let's figure out how this is going to work. Well, by this time, I figure you guys are like, I got this. It's 2 sine theta equals -1. Let's divide by 2, and we get sine theta equals -1/2. And I think about it, hey, sine is negative. I know it is, but it's not negative in quadrant 1 or 2. So my angles that I'm going to find that make this true, they're going to be in quadrant 3, and they're going to be in quadrant 4. Let's do quadrant 3 first. Opposite over hypotenuse, which means, man, this is going to be a rad 3. And that means this piece of the puzzle, this little tiny sliver here, must be a 30-degree angle. But they don't want 30 degrees. That wouldn't give me a -1/2. They want this big outer angle. Well, what is it? It's the same as 180 degrees plus 30 degrees more. So that would be, to get all the way around to here, that's a 210-degree angle. Now, keep in mind, they gave me theta, so it's going to say theta, use the interval from 0 degrees to 360. That's how they're going to write these ones, okay? So 210 degrees falls in that interval. Let's go get that other angle, though. That other angle goes all the way around, stops here, but what I'm hoping you're already ahead of me, and you don't even need to see me do this, but I'm going to do it anyway. That would then give me this guy's a little sliver of 30 degrees, because that would be a -1, that'd be a 2. This time it's a rad 3, but hey, my bow tie is paying off for me. How would I get all the way over there if this blue angle was a 330-degree angle? So I already have 2 answers. I have 2 of my answers, but I'm only done with half the question. Come on. What's this question? This guy I still have to answer. But I look at that one and I say that's easy peasy, because it says sine theta -1 equals 0. Well, I'm just going to move the 1 and say sine of theta equals +1. Well, that only happens at pi over 2. When I think of my graph, when I think of my brain going pi over 2. But they don't want my answer in radian. So what is this tippy-toppy dude right here? 90 degrees. When theta is, whoa, oh, God, I hate when I do that. I don't know. Here, whoa. No, you should have gone away. Well, this is my last problem anyway, so, quit it. Why are you, go away. Go away. Oh, it didn't go away. Okay. Can I write is the question. Okay, oh, it's disconnected. Okay, the answers are 90 degrees, 210 degrees, and 330 degrees. Why won't you let me get rid of you? Why are you in my way? Oh my gosh, that's not good. Can I write now? No, it's a text box. How do I get rid of this? Man, you guys, I am so going to look forward to having a whiteboard in front of me and having students in front of me. Can I get rid of this stuff? I don't even know. I give. I give up. I can't seem to get rid of it. So what did I tell you guys? Page, what was it? Page, help me. Page 267, 13 to 33, odd, I think I said. That's going to be the end of me, guys.